in this unit, we're going to overview some basic ideas from statistics. This is a rich field, and if you're interested in learning more, I encourage you to take a course on statistics. This is a course on probability. And here we're just going to focus on the idea of confidence intervals in the next video on significance testing, and that's going to be it for our coverage. But there's a lot more to learn about, and if you're interested, just go and find a statistics textbook or take a statistics class, and you'll learn a lot more. Okay, so the basic idea here is that we're going to assume that we've collected some data that we're going to write as random variables x1 up to xn. And let's say that this data is IID and it has a mean. So each variable has mean mu, and each variable has variance sigma squared. And what I want to do is I want to assume that I don't know the mean and variance, and I want to estimate them just from this data set x1 through xn. Okay, so this is a very basic question, something that we have to do all the time in science and engineering. I get some data and I want to calculate some parameters from it, maybe the mean. Okay, well, recall I introduced this idea of the sample mean, which was just the average of the xi, and that was an unbiased estimator of the mean, right? So its average was actually mu, and its variance was sigma squared over n, meaning that as I collect more and more data, the variance goes down to 0. So I'm getting a sharper and sharper estimate of the mean. Well, what about the variance? How should I estimate the variance? Well, the natural thing to do is just to perform what's called a plug-in estimator. So just take my data and plug it into the form of this variance function. So the way that we would do that is just average together xi minus the sample mean squared. Okay, and just like we've done with the alternate variance formula, we can write this as the sum of x squared minus the mean squared. So that you can check on your own, it's pretty natural. Let's just make sure that it's unbiased. Okay, so let's take the average of this un estimator, right? I'm just going to write it using the second form, and you'll see that I can open this and write it using the linearity of expectation as 1 over n, the sum of e of xi squared minus the mean of the second moment of, or minus the second moment of the sample mean. Okay, well, this first term, each of these is going to have the second moment, the expectation of the second moment equal to the variance plus the mean squared by the alternate variance formula. And the second term is going to be the same thing, but I'm going to have the variance of mn and the square of the mean of mn. Okay, so this is just using this formula that we've seen, from quite early on in this course. Okay, now I can actually substitute in the variance and the mean of the sample mean here, and I'm doing that. And you'll see that the means cancel out. So the square of the mean cancels out here, but the problem is I'm left with n minus 1 over n sigma squared, and this is actually a biased estimator for the variance. Okay, and you don't have to follow all of that closely. The main thing I want you to remember is that conventionally the way that we deal with this is when we want to estimate the variance. So we have the sample variance, that's this Vn, and instead of using 1 over n, we use 1 over n minus 1, and that fixes the problem. So really, that's all we have to do to get rid of the tiny bit of bias that's in that estimator that we proposed. Okay, and this is going to be our unbiased estimator. And this is just to explain to you why when you look at the sample mean, you always see 1 over n, and when you see the sample variance, you see 1 over n minus 1. Okay, so you can revisit this if you like, but it's just to introduce that basic idea. Well, here's the idea behind confidence intervals. What I want to do is estimate some parameter from data, and I want to try to quantify how close my estimate probably is to the true value. And we'll see what we mean by probably. And we're going to focus on estimating the mean for now. Okay, so let's say I give you IID random variables, x1 up to xn, and they have true mean, mu, and true variance sigma squared. A confidence interval, which we write as a, b. Okay, so some interval of the real line starting from a going to b. And these are capitalized because they're actually going to be random variables. And it's a confidence interval for the mean, mu. It has confidence level 1 minus alpha. That means that it satisfies the property that the confidence interval contains the mean with probability 1 minus alpha. Okay, and this A and B are functions of the random variables that I've collected. Okay, so they are themselves random variables. So the important thing to note from a technical side is that this probability is evaluated with respect to x1 up to xn, or rather the functions a and b, but not with mu. Mu is just a constant. Okay, so mu is a true constant. It doesn't have an associated probability. When we talk about probability here, we're just talking about the bounds of this interval, which are random functions of x1 up to xn. Okay, so here's an example that you've probably seen in many contexts. Let's say there's a polling firm and they tell you that they come and report that they've interviewed a lot of people, and 72% of the population, plus minus 2% of the voters, let's say, that they support the upcoming ballot measure. So maybe people want to pass a new law and there's a ballot measure coming up, and they say that their firm reports this with 95% confidence. So what does this mean? Well, in our context, this corresponds to trying to estimate the mean, okay, mu, which is equal to little p, of a Bernoulli random variable, and we've gotten IID Bernoulli samples. Okay, those are so basically if you support it, you say yes, and if you don't support it, you say no. So that's the Bernoulli part. And you've interviewed a lot of people, so you've interviewed a lot of people from this population, and so you have these n random variables, and so now you have this confidence interval, right? So what you've done is you've process this data in some way, and you've obtained a confidence interval that you believe contains the mean. So it's 0.7 up to 0.74, and you believe it contains the mean, and you report this with confidence level 0.95. Okay, so the important thing to know about this confidence level is it doesn't really help you understand whether this particular polling result is true or not, right? It's really with respect to an ensemble of polls. So let's visualize that. So let's say there's poll 1, we run poll 1. I'm trying to get this value between 0 and 1. In this case, the true mean was mu1, and I have a1 and b1 generated from the data, and indeed the true mean is contained in here. So I say that, yeah, okay, that was true. And this is just something I can see from behind the scenes when I'm running these processes. I never really get to know what the true mean is. I only get these confidence intervals and levels. I've run this process again. Maybe I poll about a different question. This could be a different poll run with the same kind of assumptions, but this could be a different poll about a different ballot measure or a different question. And in this case, it didn't contain the true mean. So I put an X. I run another poll. I'm a polling firm. I'm running lots of different polls. Now I run another poll about maybe another question. This time it did contain the true mean. That's true. And I'm going to keep doing this. Maybe I do this k times. Right? So I just keep repeating this process. And the kth poll, again, let's say I have mu of k, and I get this confidence interval ak up to bk. And again, it does contain the true mean here. Okay, so what's going on is the way to think about this intuitively is that if you have confidence level 0.95, 95% of the firm's confidence intervals over the long run will contain the true mean. Okay, this is the thing that's going on. So basically, you could repeat the same poll about the same question if you interview different people. Then if you did that many, many times, then you could say that it's a 95% confidence interval with respect to all those different attempts. Or what you could do is you could run polls about different questions. As long as they're in the same context, IID Bernoulli P, then you could talk about 95% of those polls confidence intervals being correct over all of those different questions. The main thing to remember is this is not a probability about the mean falling into the interval. The mean does not have probability. The interval itself is random, and that's what has the probability. Well, okay, let's get to the more practical side of this. So how can we calculate our own confidence intervals? Okay, well, what we need to do is we need to start out by making some kind of assumptions about our data in order to make any progress. Okay, and of course, if these assumptions are wrong or bad, then our confidence intervals will be wrong or bad. So the values we get won't make any sense. Okay, and we're going to focus on just a few basic methods, but there are many others out there. And, depending on the kinds of questions you're interested in, maybe those will be a better fit than what we're going to introduce. Okay, so we're going to build this up by assumption. So let's make a very basic assumption. Let's just say I know the variance sigma squared, but I don't know the mean. I want to know the mean. All right. So using Chebyshev's inequality, we know that the probability that the sample mean wanders off from the true mean by epsilon or more is upper bounded by the variance of the random variable x divided by n times epsilon squared. And the reason for that is because the variance of the sample mean is sigma squared over n. Okay, so using the complement property, we can flip this around and say that the sample mean is within epsilon of the true mean with probability 1 minus sigma squared over n epsilon squared. So the confidence interval is the sample mean minus epsilon up to the sample mean plus epsilon. And the level, the confidence level, is 1 minus sigma squared over n epsilon squared. Okay, let's see how this works through an example. That might be a little more clear. So this is actually a pretty conservative bound, and it's not one that's often used in practice, but it's just to warm up and understand what's going on. So all I need to know is the variance. So I'll just tell you in this setting, the variance is 1/4. Okay, and what I want to understand is how large does n need to be? How many samples do I need to collect so that I can build a confidence interval with this tolerance epsilon is equal to 0.05, right? And so that's going to be my confidence interval for the mean. So I'll take the sample mean and I'll allow epsilon to be 0.05. And then I want my confidence level to be 0.95. Okay, how can I figure that out? Well, this tells me, first of all, that my epsilon needs to be 0.05 because that's what's sitting in the confidence interval. And my confidence level should be 1 minus the variance, 1/4, over n, which I want to solve for, over epsilon squared, 0.05 squared. That should be equal to 0.95. So that's 1 minus 100 over n, and then 1 minus 1 over 20. Okay, so this tells me that I need to have 100 over n equal to 1 over 20. So I need to have n is equal to 2000. Okay, and that's actually a pretty high number. And the reason it's so high is that this Chebyshev's inequality makes very few assumptions about the random variable. Actually, all it assumes is that you know the variance. And usually we like to make more assumptions in order to get lower requirements for the number of samples. And let's see how we could do that. Okay, so one new way we could think about is that I can use the central limit theorem. And by that, I mean, let's say we believe that for the regime that we're in, the central limit theorem is doing a good job of approximating the CDF of the sample mean, and I also know the variance sigma squared. Okay, so I've added this assumption that I now think the central limit theorem, the Gaussian approximation, is good. So what that means is I can take the this event that the sample mean wanders off by more than epsilon, and I can write it as so root n divided by sigma times root n epsilon divided by sigma. So basically I just take both sides and I multiply them by root n and I divide by sigma. And now I'm going to try to get rid of this absolute value around mn minus mu. And you'll see why I want to do that in just a second. It's basically because I want to make this into CDF terms. So first of all, I just remove the absolute values here, assuming that it's positive. And then if I remove the absolute value in the other direction, it's like I'm assuming it's negative, and then so it has to be less than negative root n over epsilon. So you can sit and write this down for yourself and convince yourself that this is what it is. And now I can use the central limit theorem to approximate these terms with the corresponding standard CDF values, right? So I just plug into the standard CDF because now I believe that this is well approximated by that. Okay, and so then this term 1 minus the phi function is just the q function, and this other term is also just the q function. So I really just have 2q root n epsilon over sigma. Okay, and all I need to do now is use a lookup table to find the gamma such that q of gamma is alpha over 2. So thinking about this visually, what's going on is I have my Gaussian approximation and I have these two areas, right? So you can think about the origin in this case as this value that I don't want to drift away from. So basically it's kind of the center. So I've removed the mean, so the center is now at 0. And I'm trying to say that the probability of drifting away by more than this tolerance, which is root n epsilon over sigma, should be alpha or less. And so what I do is I take the left tail and I try to set it to alpha over 2, and I take the right tail and I try to set it to alpha over 2. Okay, and so what that's going to do is that's going to give me this confidence interval with epsilon equals gamma sigma over root n. And so I just plug that in and I get confidence level 1 minus alpha. So really, I get to start out by specifying alpha, Then I go through this equation, Q gamma is equal to alpha over 2. I solve for the gamma that for which that that lets that hold with equality, and then I plug in that gamma to get my epsilon. Okay, we're going to do an example, and that should make this a little more clear. Okay, we're basically just going to repeat what we were doing in the previous example, but now I'm going to add this assumption. So I have x1 through xn, and I believe that they're IID with known variance 1/4. And I also now believe that it's a good idea to use the central limit theorem approximation. So I believe that my sample mean is in a regime where its CDF basically looks Gaussian. And that actually happens once n gets large enough, so that's reasonable. Okay, so now how large should n be? Okay, such that, so I want to know how many samples do I need to collect such that this confidence interval, sample mean minus 0.05, that's going to be my epsilon, up to sample mean plus 0.05, again my epsilon. I want that to be my confidence interval for the mean. So I want my sample mean plus or minus 0.05 to contain the true mean, and I want that to happen with confidence level 0.95. Okay, so we're just going to go through the process that's outlined above to solve this. So 1 minus alpha is 0.95, and that tells me that alpha has to be 0.05. Okay, so then what I need to do is find the gamma such that Q of gamma is 0.05 divided by 2, so that's 0.025. And in MATLAB, I just use Q function inverse of 0.025, and it tells me a number that's basically 1.96. I've just approximated up to 2 decimals. So then 0.05 has to be equal to gamma times sigma over root n. I have most of these terms, so I need root n is equal to gamma squared or sigma squared over 0.05 squared. So I've just flipped this equation around and squared it so that I can solve for n. Okay, and I'm going to plug in the values I have. So I have gamma is 1.96, sigma squared is 1/4, and then epsilon that I want is 0.05. And then if I solve this and round up to the nearest integer, I get 385. So if you do this in your calculator, you'll get 384 point something. Because the number of samples needs to be an integer, I just round it up. Okay, and this is actually a better thing to have, because before, in order to get this confidence interval with confidence level 0.95, I needed 2,000 samples. Now I've added in the central limit theorem assumption, and I got it down to 385, which is more reasonable. Okay, well, one thing we've been doing here tacitly, or not so tacitly, we've been writing it out, but what do we do if we don't know the variance? Okay, so that it makes sense that we wouldn't know the variance either. And in that case, we would need to estimate it. And we actually already know how to estimate it. We have that sample variance, but what we need to do is we need to come up with some new families of random variables to deal with the resulting expression. So we actually can no longer necessarily just use the standard normal CDF. We need a couple of more ideas to make this all hang together. So we said that y is a chi-square random variable with n degrees of freedom. And the way that this is written is y is distributed as this chi symbol squared with this parameter n, if you can write it as the sum of the squares of n independent standard Gaussian random variables. Okay, maybe it's easier to see that with an equation. So then y would be equal to the sum of xi squared from 1 to n, where x1 up to xn are IID Gaussian 0, 1. Okay, and we're not going to prove any of the stuff that's going to follow. I'm just going to show you some things that we might end up using. The mean of this is just n, and its variance turns out to be 2n, and the CDF we can get from a lookup table. And this is, by the way, a non-negative random variable because it's just the sum of squares. Okay, so we're not, just like all the previous families of random variables, we're not going to derive any of these, we're just going to use them. Okay, the main thing we're going to use is the lookup table. We need one other distribution quickly. So we need that W is has a student's t distribution with n degrees of freedom. And this is written as W is distributed as t with parameter n. If it can be expressed as W is equal to z divided by the square root of y over n, where z is Gaussian 0, 1, y is chi-squared with degrees of freedom n, and y and z are independent. Okay, first of all, this student was the pseudonym for someone who is publishing about this idea about 100 years ago. So it's not referring to you, the student, but it's somebody's pseudonym when they were trying to publish, sort of anonymously. And you can go and read about the history of that. So it's just something that's hung with us, but we might just call this the T distribution. Okay, so that might be our shorthand for this. And so looking at this expression, you just have a Gaussian divided by a normalized square root of a chi-squared random variable with n degrees of freedom, just like we defined above. So now, because I have this Gaussian on top, it turns out the mean will be 0, and the variance, it's harder to show, but the variance is going to be n over n minus 2 when n is greater than 2, and it turns out to be infinity when n is equal to 1 or 2, but we're not going to use it in those settings anyway, and we're not going to worry about that. So n is always going to be larger than 2 for us. The main thing we want is this CDF, which we can get from a lookup table. And the PDF, it's worth noting that it's symmetric about 0, and it converges to a Gaussian as n increases. So in fact, the T distribution, as you make n larger and larger, starts to look more and more Gaussian itself, even with respect to its PDF, not just the CDF. Okay. Let's make the assumptions now that x1 up to xn are IID Gaussian, okay, with unknown variance. And you'll note, so the tacit assumption before was that the central limit theorem is a good approximation. Here I'm strengthening that a little bit to that they're actually Gaussian. And the reason I'm doing that is so that these distributions that we just introduced exactly apply. Although people tend to use these tests, when they're not 100% sure that it's Gaussian, and you can then, evaluate those results as you wish, but this is the assumption that's being tacitly made. All right. So the statistic Wn, which is root n sample mean minus true mean over the square root of the sample variance, has a student's T distribution with n minus 1 degrees of freedom. And to see why that's true, you can see your lecture notes. I'm not going to show that here. Okay, so basically all I'm doing is instead of trying to form this Gaussian-like random variable by dividing by the true square root of the variance, here I have to divide by the square root of the sample variance. What that's going to do, so this W of n is going to have a distribution that looks like this. It's kind of Gaussian-like, it's not quite Gaussian. What I have to do is choose beta such that this thing stays between minus beta and beta with probability 1 minus alpha. If I've done that, then I can work my way out of this and compute the confidence interval, right? So I'm trying to say that this random variable stays in this regime, this Wn stays in this regime with probability 1 minus alpha, and then I'm going to use that beta to go and solve for my confidence interval. It's often easier to use the symmetry here. So by symmetry of the T distribution, it actually turns out that it's equivalent for us to just take beta and then plug that into the CDF for this T distribution and then get 1 minus alpha over 2. Okay, so just comparing it with above. So now I've taken the left tail, which went from minus beta down to minus infinity, and I've said that, well, by symmetry, that has to be equal to what's in the right tail. So then it's like I've lost alpha over 2, right? And so now I can just solve this equation, which is a little bit easier to look up in a lookup table or plugging into your favorite numerical software. So usually we just say, take the inverse CDF for alpha, 1 minus alpha over 2. So once you have this beta, all you're going to do for your confidence interval is take the sample mean minus beta times the sample variance over square root of n, and that's going to be your tolerance, okay? And your confidence level is going to be what you choose, 1 minus alpha. So you pick alpha, then you go and use this inverse T distribution CDF to find beta, and then you just plug that in along with your sample variance and square root of n, and then you're set. Let's do an example. So for my example, I'm going to assume that x1 up to x8, so I'm just going to get 8 measurements. I'm going to assume they're IID Gaussian and that their mean and variance are both unknown. And I'm interested in just the mean, but I need to compute the variance in order to proceed. Okay? So what I'm going to do is compute a confidence interval, just like we've been doing, for the mean. And I'm going to decide now that the confidence level is going to be 0.9. Before we were using 0.95, now we're going to just use 0.9. All right, here are my observations. I'm just going to write these down for you exactly. So they're going to be x1 is 2.7, then 7.0, 4.7, 3.9, 4.7, 3.8, 3.9, and 5.5. This could come from anything. Maybe you're trying to measure the dimensions of some part you've manufactured. Maybe you're trying to measure some kind of biological process. Doesn't matter. So like you've collected some data and you want to know the average of that data and you want to put a confidence interval around it. That's what we're doing. So I've got this data. And by the way, just for the purpose of the example, I'm assuming that these are the exact values I've gotten, although everything else that I'm writing, I'm just writing for 2 decimal places, but it might actually have more in the representation. Turns out the sample mean in this case, if I just average these numbers, will be 4.53. And the sample variance, if I just use the sample variance formula, it'll be 1.68. Okay, now I can kind of proceed. What I do is I take beta and I try to find beta such that the inverse CDF here is equal to 1 minus alpha over 2. So that means that it's equal to 0.95, right? So I asked for confidence interval 0.9, but I need to make it a little stricter because I'm absorbing this left tail like I did above. In MATLAB, the way that I would do this is I would call the T inverse function, and I plug in 0.95, the number of variables I have, minus 1. Why do I have minus 1 there? So really what I'm plugging is 0.95 and 7. Because this WN statistic has a student's t-distribution with n minus 1 degrees of freedom, not n. Again, we're not showing that here, but I'm just telling you that you need to subtract 1 for this to be correct. And you get 1.89. And now I'm just going to come and plug this in. So here's a different way that you see confidence intervals written from time to time. You might report the exact value of the sample mean and then write plus minus this term, which is 1.89 times the square root of 1.68, the sample variance over square root of 8. And we can simplify this number down to be 4.53 plus or minus 0.87. Okay, so this is a different notation. It's still an interval. So it's the interval that starts at 4.53 minus 0.87, goes all the way up to 4.53 plus 0.87. But this might be an easier way to understand what that's saying, right? So we've computed that confidence interval. Okay, so now we're just going to end here by doing one more thing, which deviates a little bit what we've been saying. So we focused on the mean, but what if we want to build a confidence interval for something else? Okay, so maybe I have some other parameter or function I'm interested in. Let's just look at the variance. Okay, so we'll just end by looking at confidence intervals for the variance. Let's say x1 through xn are IID, Gaussian, and they have unknown mean and variance. I don't know the mean, I don't know the variance, I want to know the variance. Turns out the statistic yn, which is n minus 1 over sigma squared times the sample variance. So if you write this down, it turns out this has a chi-square distribution and it has n minus 1 degrees of freedom. Again, we're not going to show that here. You can see your lecture notes for why that's true. Okay, so here's what that distribution, chi-square distribution, actually looks like. So it's non-negative. And what I need to do here is I need to, again, set some bound so I can get my confidence interval. So I need to select 2 points, T1 and T2, such that yn lives between them with probability 1 minus alpha. Okay, so here they are, T1 and T2. So I want this area to be 1 minus alpha, so I can have my confidence level. The way that we're going to do this here is I'm going to set T1, the left interval, so that yn T1 is up to alpha over 2. So the left side of this is only alpha over 2. That's just my choice. That's how I'm doing it. And I'm going to set the T2 such that the CDF is equal to 1 minus alpha over 2. Okay, so this kind of starts at T2 and it's kind of absorbed everything to the left, right? And so it goes all the way to the left. And the reason I've done that is so that I can reuse this CDF function, right? So those are the 2 things that I need to keep in mind. I'm going to pick T1 so that when I plug it in, I get alpha over 2. And I pick T2 so when I plug it in, I get 1 minus alpha over 2. And then my confidence interval will just be the following. It'll be n minus 1 times the sample variance over T2, and then n minus 1 over this times the sample variance over T1. Confidence level is whatever I want. I pick alpha. So let's come back to the same example So this is the same example that I had on the previous slide. I just pasted it again for you to see. I've already computed the sample mean. I've already computed the sample variance. The last thing I want to do is I just want to compute a confidence interval for the variance now. Okay, so I'm going to follow this process that I laid out above. I'm going to pick T1 so that the CDF at T1 is 0.05. In MATLAB, the way I do that is I call chi2 inverse for 0.05, and I'm going to use 7. Why do I use 7? Remember, just like on the previous slide, I had n minus 1 degrees of freedom, and here I have 8 points, so that's 8 minus 1 is 7. Okay, so that's going to give me in MATLAB 2.17. I'm going to do the same thing. I'm going to call it to get the value T2 to be 0.95, like it says above. And so that's 1 minus alpha over 2. So I plug in 0.95 and 7, and I get 14.07. Okay, now I'm going to compute my confidence interval by plugging in these values. So as before, I'm going to have n minus 1, that's 7, times the sample variance, 1.68, divided by 14.07, the value I got from T2, and then divide by 2.17, the value I got from T1, and that gives me 0.84 up to 5.43. And that is it.